Alright, making a draft science video, I think. Yeah, put it there. You're just sort of in the mood to talk about this, how this physics stuff works. Yeah, it's not really relevant. I mean, we really should talk about maybe biology and go over the consumption and reproduction thing forever, and the psychology thing, you know, that we're just owned by a bunch of stupid passions and addictions. But anyway, we're going to do some physics instead. Just because, you know, people look, they find a way to make the physics turn into something. It's like people have tried, I've said before, but I mean, they try to bend biology, try to get there to be some sort of mother nature in nature, you know, as if we have more control or power, or that we have more prospect or hope to make something out of life. Oh yes, that we can just take out all our native competitive nature or some other crap and still come up with some sort of equation that makes sense. And yeah, I don't think you can do it. But anyway, physics. So I'm thinking about this whole unification thing. Yeah, that's right. Oh yeah, where Einstein failed, you know, a stupid failure like myself is going to step in. But you know, whatever. I can play with it. There's no rule against me playing in physics. So anyway, you got these three. Basically, there's three things that run the universe. I mean, there's three forces. Let's say. I mean, there's the gravity thing. There's the electricity thing. And then there's the nuclear forces, which are only really understood because they kind of, it would appear, completely negate our control or overwhelm the electrical forces. So electricity, you know, basically distance-wise, per distance, is much more powerful than gravity. You know, gravity's for big mass. Electricity is kind of like this level, and then, you know, on the atomic level, these nuclear forces have the same. You know, just as electricity can create a much more influence on a body in close proximity than gravity. Nuclear forces trump, you know, electricity by, you know, orders of whatever, 20 or 30 magnitude. That's why, you know, nuclear bombs are so goddamn explosive, is because that when you release that built up force, that potential that exists, that's overwhelming those electrical forces, and you essentially liberate all the electrical forces being suspended by the nuclear, by the nuclear forces. Yeah, it's just a tremendous amount of electrical energy. Yeah, that's sort of what it is. But I mean, it's you've got to consider it a release of nuclear energy because it's that release. But what's being released is the controlled electrical forces. Yeah, I think so. But anyway, I have to do some math to figure that out. But anyway, that part's probably not critical. I guess the critical part for just getting your head around it is to figure that those are the three things you've got to try to wrap into a single theory of physical forces. So you've got gravity, electricity, and whatever's holding nucleuses of atoms together. And presumably, well, I was going to say electrons too, but I don't know if they're held really with nuclear forces. That might be strictly electrical forces, but whatever, doesn't really matter. So anyway, it's the nuclear, inside the nucleus is where you got this mystery force, the one we can't really get a good view of that one. And our view of electricity is, you know, it's better, but it's not exactly in our face either. I mean, we see it with lightning, but you don't see it, you know, all around you. You don't see what's happening every time you interact in your environment, how the electricity potential is changing, how you're shifting all the time. So anyway, where am I going to go with this? Because I don't know if you know, it's just you've got to break it down into which thing is doing what thing, you know, how, I mean, it is curious. So there's this conservation thing also in, you know, you have this conservation of energy, conservation of a lot of things. Holy crap, that was almost fatal. But you also have a conservation when it comes to electrical forces. I mean, you can't acquire one without essentially taking it from somewhere. So it has to be, something has to give up electrons for you to gain, if you're a conductor, a charge, or for your potential to be changed, something else's potential has to change, I guess is the rule. I mean, you can't impart it without taking it from someplace. So something becomes positive because something else becomes negative, and vice versa. Yeah, I'm pretty sure of that. Anyway, I know it's in there somewhere. Yeah, I really do think that's true. Conservation of charge. Yeah, I think that's how it goes. Whatever, it doesn't matter. It sort of does matter, but I'm not going to worry about it right now, because I'm just talking out loud. and such. Draft science. Anyway, all right. So now where do I go? All right. So yeah, just with electricity. Okay, so you got this. Electricity is a lot like gravity. I mean, it's got a lot of the same kind of patterns to it, but it's got this weird, opposite thing. So it doesn't. It not only creates this attraction, but it has this repulsion mechanism. There's no repulsion mechanism in the universe as far as we know, except when it's creating some other substance. It's producing a ton of photons, or it's producing some sort of force made out of something else, out of nuclear or electrical particles. There's no repulsion force. There's just gravity. But with electricity, you got this attraction force, and the repulsion force. And that's sort of interesting. There's a way we've sort of diagrammed things as this plus and minus, and so they attract each other, the opposites. And then if you have plus plus, they're repulsed, and if it's minus minus, it's repulsed. So you have these two states that you have three states you can be in: plus, neutral, or minus. And I guess it was always kind of confusing. They say Franklin guessed wrong in terms of which one is negative and positive, and I guess that we've demonstrated that sort of through ions. You create an ion that has an extra electron versus one that is short an electron, an atom, and that's how you create a conductor, is having something that's either short electrons or something where electrons are very mobile. They can move easily from one atom to another. So that's why there's some things that conduct electricity and some things that don't, is because they have loose orbits. No, that's not a good way to say it. There's a mechanism that allows electrons to bump each other out of orbits. No, that wouldn't be good. There's got to be a way to say that. But the orbits are somehow the orbits. See, that's right there we're in trouble, because that's just theoretical stuff. But the glue, see, that's just not going to work either. How to describe that? I have to think on that one. There's probably, I know they figured that part out. But anyway, just between a conductor and a non-conductor is the fact that the electrons can, like you throw it to me, I throw it there, somebody throws it there, it moves through the substance. And either by, me giving up one of mine because I got one, or just allowing it to transition through me. Yeah, sort of. All right, but anyway, that attraction repulsion thing is kind of interesting, because you got to figure out even the gravity thing. This is a key element that I want to get to. It's way too late in this video to get to. Is how do you explain that? How do you explain it? How do you come up with some sort of model, some sort of mechanical, physical, particle kind of model that fits into our brain, that explains that movement? What's inciting it? How is the pressure? How is the movement animated? We can understand it's a force. We can understand, how the force can't come from nowhere and all that kind of stuff. But what we have to be able to describe is what's the exact mechanism. How is it done? What is there some invisible substance in the universe that's being thrown at something that they're throwing at each other and that repulses them, and vice versa, where there's something they want and the universe is pushing them from behind? When there's an attraction, it just means that the back pressure is stronger than the forward pressure, like an air pressure. If you have more pressure, like with an airplane, it'll lift the plane because there's less pressure above the wing than below the wing. That's very. See, yeah, we did explain airplanes. They seemed mystical at one time, and then we came up with a mechanical explanation. But they're in our piece of the universe. They're in this size piece part, and so it's likely that we could come up with something that fit in our heads. But going into this tiny part, that's where it gets tricky. Is we have to be able to visualize something, a basics, a foundation. So. How you doing? Beastly little kids. Oof. Yuck. Yeah. Oof. Oof. Feel the cooties. Yeah, it's like they radiate it. But you know what a cootie is, so that's easy to figure that out. I don't have to. That's not complex physics. Cooties flying through the air. Yeah. Anyway, that's as far as we'll go in this video. So yeah, I don't know what point this will have, except that I'll put these together and then I will review them in the future and try to critique and put them into something more concise as I think further and come up with little pointed pieces. The little pointed piece here is 3 things have to be reconciled: nuclear force, electrical force, and gravity. And the weird thing is what exactly is the mechanism of this attraction-repulsion thing, as gravity, or as electricity, or as a nuclear force, which is going to be a lot harder to see. But anyway, so that's the bullet point. Point on the bullet. The bullet's really weak. Anyway, something like that.